being recorded. Which is sad that that's a thing I'm excited about, but that's all right. Now I'm deeper into double digits. Good. Does anybody have any questions from homework or in general or anything? All right, let me show you guys something. I promised you something earlier this semester. I'm going to show it to you. We now know enough. Yes, we now know enough to have. What am I showing you? Can you guys see Desmos? And by the way, I think I showed you the other day. You go here to change it to polar. You could do this on your TI calculator also. That equation though, exactly. So it's not even the whole thing. If you want to play along, go ahead and put this equation in your calculator, in your calculator. I did start the recording, right? I already forgot. Yes, you did, Jeff. It just happened and it was out of your brain. So here you go, e to the sine theta. Isn't that cool? I think somebody asked me about this and we did it. I can't remember now.
I asked you something similar, yeah.
Yeah. So I was kind of like, oh, that's funny that you're asking me. And then minus 2 cosine 4 theta plus, now all the, look at this, and it's to the 5th power, that whole thing. Sine of 1/24 2 theta minus pi, all to the 5th power. Now, guess what you get if you do that? You get something that I promised since before the class started. I promised to show you the equation to make a butterfly show up on your graphing device, whatever it is. So somehow this math equation translates into what we would interpret as a butterfly. Is there a way to change the color? I have no idea. No, I can. Cool. I got a purple butterfly. Purple butterfly. Ha ha. Oh, sorry. Oh my goodness. I have to apologize ahead of time. I'm a little tired. I tend to get even more goofy when I'm tired, and I'm sorry. I'll try to keep it in check. Okay. Is that all right for anybody? We're gonna actually develop a slightly better equation for it, because you see how the head is a little messy. I mean, it's not a perfect butterfly, but if you kind of scroll out, it looks pretty good, right? All right. And is this really surprising that we could do something like this now that we have this system that loves curves? No, it's not that surprising. Oh yes, so see how I let mine go from 0 to 12 pi? I don't think you have to go that far, but I just let it go. Yeah, you can go further. Watch, let me see if I go further than 12 pi. Let's go 24 pi. Look at that sucker. Now, if you just go to like 6 pi, you get like it's an evolving thing. It's like a, no, Jeff, don't say Pokemon. It's evolving. Yeah. And what's really interesting is if you change one of the parameters and see what it does to the equation. See what I'm saying? If I make that become 24, what if now this is going to be a huge change. This should really throw it off a decent amount. If I make that a 5, look at that. That is no longer a butterfly, but it is neat. What if I made it 3? Jeff, that's not a 3. There you go, buddy. Look at that. Look at that. But 4 is the one that makes it work pretty well. Anyway, sorry guys, sorry. I just wanted to make sure I closed that loop, right? I'll show you what that equation is. I kind of teased it way a long time ago. So now we've done that. Okay, let me make this all about me. Looks like Austin's got the spotlight. I just took it away from him because I have all the power. Anybody have any questions now that I've wasted a little bit of time? You guys doing okay? I keep asking that question, but are you okay? Okay. And I'm not, let me see, what do I have up here? Oh, who's talking to me? Number 5 on the quiz. Okay. Hold on. Where's this at? Oh. Oh, where are you, quiz? All right, hold on. All right. Whoa. All right, here we go. A reminder from 9-5. Okay. Okay. Well, hold on. There's too many things at once. So Jordan, I want to make sure. Are you talking about number? Oh, yeah. That's right. You're talking about the number 5 we talked about earlier from the practice quiz, right? Okay. So we'll do that now. If there's no other questions on the practice quiz, I apparently last semester's Jeff, he's an asshole. He didn't finish the whole practice quiz. So present day Jeff is going to do that right now. So if you get the practice quiz, it's practice quiz 10. Just to remind you guys. So here it is right here in unit 10, practice quiz 10. I apparently did not do number 5 yet. Here it is. Solve the triangle kind of stuff. Number 4 is from, isn't number 4 the one from 9-5? 9-5 was solving trig equations, right? So number 4 is the examples from section 9-5. So let's do this. So we got this somewhere. Can you guys access that so I can close this down? Let me see, how do I want to do this? Let's do it this way. Oh my God, so many buttons to push. It's insane. Every time I do this, it takes a little longer. There we go. Okay, now, so let's see, let's take a look here. Let me open this thing up. So I'm going to do number 5 from the practice quiz. And let's see what it says here. Oops. Oh, I see what you mean. Okay, understood. Hold on, let me get back to this. Okay, here we go. So I've got to solve this triangle. Solving the triangle means finding all the unknown angles and unknown sides. So you're going to do the whole thing. Oh, let me turn this on. So help out a little bit. No, it's worse. Get there eventually. All right. So they give us, let me slap this down and maybe I can make it roughly look like it makes sense. I'm going to call this A, I'm going to call this B and call this C. This is 42 degrees, they tell me, angle A. They tell me side B is 6, and they tell me side A is 8.1. Now, can somebody tell me what law I should use for this? Which law is going to work?
Sine.
Yeah, law of sines. Why?
We have one complete
Good.
pair.
I got a complete pair. I got a complete ratio I can make. I really want you guys to understand. That saves us from having to go, okay, SAS and SSA and blah, blah. Oh my God, I don't want to remember it that way. It's so much easier than that. Law of sines is all about ratios. If I can't make a complete ratio, I can't use law of sines. Bam. If I cannot use law of sines, I will always be able to use law of cosines and vice versa. It's kind of nice. Okay, maybe. So what's the ratio I can set up?
Sine of 42 degrees divided by 8.1.
And what's the angle that I have to find first?
Sine of b over 6.
Yeah, because that's the only one, this one I don't know anything about. So I got sine of b over 6. Jeff, why will you never learn to write smaller and more concise? Okay. Someday. I've got such a tiny little freaking, your triangle's huge. All right. So I got sine of 42 degrees over 8.1 equals sine of, I don't know, over 6. All right, so
Sine of b is equal to 6 sine of 42 over 8.1. I think I did that right.
6 up, I like it, yeah. 6 sine 42 over 8.1. Are you getting a little tired there, poor little marker dude? So let's see what we get for this. Amanda, you okay?
Yeah.
Okay. Oh, shit. And learn from Jeff. Learn from Jeff. And you're all like, well, that's what we're here for. But learn from Jeff's past mistakes. Make sure you are in the correct mode, right? If you're not in degree mode, if you're in radian mode, it's going to think this is 42 radians, which is bad. So make sure you're in the right mode. Did somebody get that angle yet?
It's approximately 29.71.
Yeah, I like 29.71 degrees, that's fine. And I'm going to put here B1. All right, because what could B2 be?
$150.28.
150. Yeah, so B2 could be 150.2829.
But that's not possible, right?
Beautiful, because what's the angle that I already, everybody with me? Is everybody with what's happening?
Yeah, because the two angles you already have are greater than 180.
And inverse sine could give me a reference angle. So if this is here, the other possibility is there. 180 minus this is that. But 42 does not work with that. Not only is there nothing left for him, that's already taken up more than it can. It's over 180. That's not going to work in our geometry. It works in other geometries. But don't worry, that's a little bit higher math. Don't worry, we're not going to do that. All right. So thankfully, I don't have to worry about a separate second triangle. Now, the bad thing about my practice quiz, I should have made one that actually had a second triangle work, because you know I'm going to have a second triangle problem. You know it. You know it's going to happen on the quiz. There will be a second triangle, right? You just know it. You know it. I'm telling you right now. Don't forget to check for it. Which law do you have to check for? Obviously sines, because that's what we're doing right now. So I'm not going to call that B1 anymore. It's just B. What's C then? What's angle C?
108.29.
108, yes, 0.29 degrees. Everybody cool with that? 42, 29.7. Leaves over this much for C. And now the only thing I don't know is side C, right? Technically, you could use law of cosines if you wanted to, but why would you? Right. So, everybody, you guys okay out there? Can you do an example? Oh, okay, sure. We'll do an example of a second triangle. All right, what was I doing? I figured, God, I'm really out of it. So how do I find side C? What do I do?
Plug it in.
Plug it in to what? So I've got my
Oh,
nice.
sorry. I wrote out the full thing first, but it's sine of C is equal to, or over C is equal to sine of 42 over 8.1.
Yeah, sine of 108.29. There we go. Over side C. I like it. Now, technically, you could have used this one, but the reason I don't use this one is one, I might have been wrong with this, well, which would make that one. But two, more importantly, this is an approximation, right? And this is something I know exactly. So I don't want approximations on that. It doesn't really matter. But so if I solve this for C, I'm going to multiply this up, divide this down, multiply that up. So I get 8.1 sine of 108.29 divided by sine of 42 degrees. And I throw that shit in.
11.49.
Okay. Did everybody else get that same thing?
Yes.
Good, because I'm not actually doing that. I'm getting ready for the next thing I'm gonna do. And say it again, what'd you get? 11.51? 11.49? 11.5. All right, we'll just split the difference. I don't know, people might have rounded differently, I have no idea. All right, I like it, I like it. Now, real quick, all right, so everybody got this? I'm gonna erase this. Somebody requested an example of a second triangle. I'm going to change one thing in our original triangle, and it's going to make there be a second triangle. I believe. We'll find out. Maybe. Shit, Jeff. Maybe I'm going to have to think about this. All right. All right. Let me see what I can do. Maybe I should just start fresh. Let me think. All right, maybe, I don't know. Here it goes. Here it goes. All right. So let's see, can I create a triangle that will allow, let's see what I can do here. So say it's 21 degrees. Let's say this is 7. Let's say this is oh, you can do it, Jeff. Yeah. So let's say that this is 6. I don't know. This could be iffy. This is not the quickest thing to try to do out of nowhere. 6. Some of that. Yeah. Okay, sorry. All right, I just barely made one that works. Okay. If I did this right real quick. So already got what I'm saying here. So let's go ahead and call this C, B, B, A. Okay, doesn't really matter, but that's all right. What did I put you down for? You're my only good marker. Are you good? Can you guys see that? Yes. So obviously the ratio I can make is here. So that's sine 21. Is that all right? Probably not. Shoot. I'm gonna have to stick with you. Sine 21 equals over 6 equals, and got to go for B because that's what I know something about. Sine of B over 7. Okay. So if I really want you guys to be okay with solving this very quickly, multiply the 7 up, take the inverse sine. Not a lot happening here. Inverse sine of 7 sine 21 over 6. All right, is that what I did? I really hope so. Yeah. Yay. You guys with me? Normally, people kind of like law of sines and cosines because it's right in the middle of a lot of weird shit. And this isn't quite as weird, you know, it's a little more recipe-ish. This is the only part of this that's weird, is the possibility of a second triangle and knowing when to check for it. So yeah, that's what I get too. I get 24.71 exactly. So we'll call that B1. All right, let's see if anybody wants to work. All right, you look good. Oh yeah, good Lord, I can get high on that. So what might B2 be? Right, a little perks of being a teacher. Dude, all right. I better stop doing that. There's only a second triangle. Yes, good, good, good. I try to really make this clear before, real quick. Inverse cosine, who remembers? Inverse cosine goes from what to what? I really need you guys to memorize this. You're supposed to know this. Inverse cosine range goes from what to what?
Minus pi over 2.
No, that's sine. So inverse cosine goes from 0 to pi. The angles in a triangle can have what radian measures? From what to what? Angles in a triangle can go from what to what?
0 to pi.
0 to pi, right? 0 to 880 degrees, so 0 to pi. So see how inverse cosine matches exactly with all possible angles in a triangle? That's why law of cosines would never allow for a second triangle. You can't. They're not reference angles. They're all, every angle I want to get would come right out of my inverse cosine. Inverse sine, like Rio said earlier, he was just getting ahead of me, goes from negative pi over 2 to pi over 2. So part of those are going to be reference angles, right? And it could be in the first quadrant or the second quadrant. So that's a problem. So that, and there's also geometric arguments you can make. And remember what I did? Remember this thing? Wee, 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 wee. All right, sorry, little dude. Stop. I'll stop playing. Yeah. All right. All right, anyway, so that was a geometric argument as to why visually it makes sense that there would be two triangles. The things that I know, so I can use law of cosines, would not allow for that to happen. So there's a geometric argument, and then there's actually a simpler inverse trig range argument. Now, what might a second B be? Yeah, 155.29, I think that's right. Does that leave anything over for C?
A very little bit.
Very little bit, but still something. This is what I meant. I made one up and it just barely qualified. What's left over for angle C in this case?
It's like 5.5 or something like that.
Did I do it? No. What did I do? It's 3.71, I think. Is it? 155.29 plus 21. No, I did the wrong thing. Did I? No, I didn't.
No, I think you got it right. I was looking at the wrong thing.
Yay. I'm kind of downing myself. So it's 3.71 degrees. Yeah, just barely. So obviously this is not drawn to scale. Well, that option would be this. You see, now watch. If I draw this like this, isn't that insanely small, that angle? I really want you. So if I swung this over, doesn't that make that angle C very small? Look at that, tiny little dude. Look at him, tiny little angle. Tiny little angle. I love it. Even though my picture's not drawn to scale, but oh well, it's close. Anyway, it's close enough. So let's finish out this first one. What is C1? Let me do this in blue. Let me keep this all straight. That one we've got to finish in a minute. Let's finish this option first. What's C1? If B is 24.71, what is C going to be? 21 plus this. What's left over for that?
$134.29.
Yes. So for this first triangle, what is the only what's left for me to figure out? I got all my angles, right? I was given A, I got angle B, I got angle C. I got side B, I got side A. So the only thing I have left to figure out is side C, right? Okay, so now I can set up my sine 21 degrees over 6 equals sine 134.29 degrees over C. And then I can figure out what side C is. Let me make it C1. Okay. Kabam. Oh, okay. So Amanda, watch this. If B is this, and I know A is 21, 21 plus this leaves that much to get to 180 total. Does that make sense? If I know two angles, I just do 180 minus those two to get the third angle, right? That's it. That's all there is. Yeah, I know. I might do a poor job of making sure everybody understands how simple that step is. There's not much to that step. It's just what's left over for that guy. Now, if B was actually this instead, this plus this leaves that much left over for C. That's a big ass angle. And now what do you guys get for side C?
Around 11.99.
Yeah, what did I do it? Yeah, 11.99. I like it. So now that's been solved. I know all three angles. I know all three sides. Now I just got to figure him out. And again, it's really the same work I just did. It's still C I don't know. But when I set this up now, do it in red, Jeff. All right, Jeff, shit. Sine 21 over 6 equals sine of 3.71 over C. So now when I solve that for C, I'll make it C2. I'll get the other possibility. So it really is, here's one triangle, and the blue is the other triangle, where this thing just swings in. Not really drawn to scale, but that's all right. Oh, what do I get?
I got 1.08.
Yeah, little tiny thing, little tiny side, little tiny. All right, so there's the two triangles. When you do the work, please, dear God, make it easy to follow. Don't have this stuff showing up in the middle of this. Have one triangle and have other triangle, right? That'll help you, that'll help me. Just make everybody happier. Okay. Oh, we still got to do 5B, right? From the practice quiz. All right. Is everybody good with that one? Okay. Uh, 5B gives us A is 6.3, B is 9. And angle C is 105. Okay. So now I just got to figure out the rest of it. It's kind of you know, I'm going to have to use law of cosines because we just did one with law of sines, right? And this is the practice quiz. I got to give you problem like everything. So Arian, well, how can you identify its law of cosines very quickly? Because there's no complete ratio I can make. So what's law of cosines look like? Well, it looks like Pythagorean theorem with AB cosine C. So it's this times this cosine of this angle. You guys okay out there? Okay, so now I can do a squared plus b squared minus twice AB cosine of 105 degrees. Might as well just figure out what C is. Bam. I got something. And yet again, I'm taking up so much board space. Oh, too bad. Man, it sounds about right. What is that? So I get 12.25. We get Christmas. Do you guys know? We got Christmas is the answer. Okay. No, yes, maybe. Okay. That's not. Now how the hell am I gonna get the rest of the shit? What do I still not know?
Angles A and B.
Yeah, and what do I have to use to get those? Can I use law of cosines?
You could use law of sines now.
Actually could use law of cosines, but law of sines is just so much more compact, right? I don't want to, why would I do this? And some of you guys, you got to be careful. Like in section 10.2, I know it's law of cosines, but there will be problems in 10.2 that need law of sines because we know law of sines by the time you get to 10.2. So they start to mix it up a little bit. So now I'm going to
The chapters are retroactive.
Yeah, yeah, exactly. I'm going to do sine of 105 over 12.25 equals sine of A over 6.3. I don't trust myself today. Did I put that in there right? Looks like it. All right.
29.79.
And then to figure out angle B, I can do sine of 105 over 12.5 equals sine B over 9. Or why am I doing that? All right, you guys should really be saying, Jeff, what the shit are you doing? Well, this is a nice little check. What's the smarter way to get angle B?
Just simple subtraction.
Yeah, just freaking figure out how much is left over. I don't know. But if you do all that, you'll get the right answer also. So 105 plus 29.79 is 134.79. And what's left over is what you would get if you do this, which is 45.21, I believe. You didn't have to do this. Everybody with me? I just temporarily got law of sines happy. But the minute I have two angles, the third angle, I don't need a law of anything. Right, okay. All right, so that completes that. The rest of that is on the solutions video, which is up there. Okay. Let's see. Now, there's something teased in the back of my brain. Was there any leftover questions somebody asked me that I forgot to get to? Is everybody okay?
Something about review of 9.5. Oh, never mind.
9.5 stuff. Okay, like 4B specifically, right? I guess from the. Oh, has everybody got this? Hopefully. Yes. Okay. So that one was cosecant 5 theta equals 2 sine 5 theta. I love it. Isn't that yummy? So what the hell do I do with this? Yeah, I do say yummy. You're right. I do. I just have to be in the right place. The right creep meter. I guess my creep meter got high enough. I can say, is this yummy, kids? This is such a yummy problem. Let me ask you this. How do I say this? If you have a problem like this, x squared minus 7 equals 2 plus x squared, what's your primary concern to solve this?
The exponents.
Well, what would you do first to solve this? Or let me do this. Okay. What would you do first to solve this?
Get the x's on one side.
Yeah, here's the term with your variables in it. You want them together. All right, so I want to somehow, not by subtraction either, because that's not how trig functions really can operate well together. Cosecant, isn't that 1 over sine? Yes. Can't I multiply sine 5 theta and divide by 2? So I get sine squared of 5 theta equals 1/2, maybe. Somebody see how I got there? That's 1 over sine, multiply sine up, divide 2 down, bam. All right, now what do I do?
Square root.
Square root, that's another reason why I made those squares. You would have taken a square root to get rid of the x, the square in the x, right? So here, take a square root,
Plus minus.
plus or minus, I like it. So sine of 5 theta equals plus or minus 1 over rad 2, which is plus or minus rad 2 over 2, right? Depends on how you have it memorized. So what does this angle equal?
Sine inverse.
Who cares? You don't need sine inverse. What angle gives me an output of rad 2 over 2?
Pi over 4.
Pi over 4. Now, before I do this, pi over 4, but where else? Where else? So pi over 4, where else? Why do I always make them so tiny in the corner? Here. So pi over 4, where else do I get rad 2 over 2? Go ahead.
Minus pi over 4.
Give me 0 to 2 pi. What's this? Wouldn't that still give me Would that give me positive rad 2 over 2? Yes. What angle is this?
3 pi over 4.
Pi over 4. What else?
5 pi over 4.
Pi over 4. What else?
7 pi over 4.
7 pi over 4. All right, good. Now, do you remember how we had multiple and we did plus or minus 2 pi k on all of them and all that kind of stuff? Do I need that? How far is it from here to here? Do you guys remember doing this? How far is it from here to here?
Half a pi.
Good. And isn't this the same? Isn't this the same? And I really want you to understand. You got to remember what we did. If it was just this, I would do this plus or minus, stupid book, 2 pi k. If it was just this and this, I would do this plus or minus 2 pi, and then this plus or minus 2 pi k. But since it's all 4 of these, do I need to do a statement for all 4? No, I can do one statement because if I turn this much, and if I turn this much again, and keep going, I capture all of them. So pi over 4 plus or minus, not 2 pi k, pi over 2. Okay. Okay. And then the last thing I need to do is I haven't solved for the variable yet. What's the last thing?
5.
Divide by 5. I like divide by 5, divide by 5, divide by 5. I get pi over 20, give or take pi over 10 k. Bam. Now, so part of it is get this, and then I say get 0 to 2 pi. Well, we already listed those, right? Those are the answers from 0 to 2 pi right there. You guys okay out there? Or are they? No, they're not. Let me be more careful. Those aren't the answers. That's the halfway step, Jeff. How do I take this and get the answers that show up between 0 and 2 pi? Let's see, if k is 0, I get pi over 20. If k is 1, let's make this, all right, I really want you guys with me. Do you remember having to do this? All right, I'm with you, I'm with you. I want to keep going. I want to let k grow and grow and grow until it gets beyond 2 pi. So if k is 0, I get pi over 20. This is going to be a lot easier if I make this 2 pi over 20, because now this is easier to add. If k is 1, I get 3 pi over 20. Yes? Now you see the pattern. I just keep adding 2 pi over 20. 5 pi over 20. You can reduce that. I don't give a shit. 7 pi over 20. Oh my God. 14 pi. No, Jeff, you made too big of a set. 9 pi over 20. 11 pi over. Oh, where do I have to stop? Where do I stop?
40 pi.
Well, right before that, of course, aren't these all odd? So I'm going to stop at 39 pi over 20 because the next step would be over 2 pi. And this is a perfectly fine way. Establish a pattern, put dot, dot, dot. You don't have to write. You can establish a pattern, do dot, 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 because the math is all about patterns. So that's fine. I have no idea what past Jeff did. Hopefully he did something like that. Okay. Oh. All right. Is that all right? You guys hate that? That sucks. No opinion? Okay.
It's not so bad, I guess.
The trick is, don't worry that this isn't just theta until the last step. You pretend like that's just theta and you do it and you do it and you do it and you get here. And then the last thing you do is kill that pi. All right. All right, I'm going to kill this. And do you see how? All right. So let me go back to the mistake I made earlier. If that wasn't 5 theta, wouldn't these have been the only answers? between 0 and 2 pi, correct? Since that is 5 theta, wouldn't that take the sine wave and make it really compressed? Are you guys with me? It would make it like, yes, remember that? So then a lot more shit is going to fit between 0 and 2 pi. And you can see there's a lot more shit in there because it kind of pulled them in. It pulled them in to be between 0 and 2 pi. Okay. Okay. All right. I'm going to resolve this. That's related to what I'm about to do. Okay. I'm about to go back. I decided to just do what I was trying to do yesterday. We're just going to go back and do it a traditional way. I got to work on the other way a bit. I still think I can make it work, but so let's say, so just to kind of review a little bit. So Z is the variable we use for complex numbers, and they normally come in this format, but we have determined how to make it into this format. Okay. Everybody with me? No, nobody's with me. All right. Yesterday we figured out that if I wanted to do Z to the n, that would be R to the n cosine n theta plus I sine n theta. Now, so if I saw this, now let me take this step back. Hold on. That's the result, but let me write it like this first. Isn't this, if Z is, now stay with me. If Z is this, Z to the n is this, Jeff. I don't know why I'm putting that there. Okay, there we go. To the n, yes? Right, if I raise one side to the n, I better raise the other side to the n. And this we determined yesterday. This is not obvious. We had to work on this. We had to prove it. There's no algebraic rule. It's because of the way trig works that you can do this. This is not obvious. You don't go, well, of course the n multiply. What the shit? But we saw why yesterday. Now you better do that, buddy. There you go, buddy. Good job, buddy. I'm not your buddy. All right. So now watch this. This is kind of cool. So if I saw this somewhere, I would know it's actually this to the nth power, correct? Because that's what that says. If I saw this sitting somewhere, that would mean it's this. I could write it like this, right? Okay, let's keep that in mind. Okay. So let's start with this. I'm going to do some really kind of strange shit here. Here we go. I'm going to keep myself straight too, because I wrote this down. All right. Isn't this also equal to? Tell me if this makes any sense. I think I did this yesterday, but it was kind of in the middle of some new way to do things. But so this part's fine. Does anybody have trouble with what I just did? Did I just change things at all? If you have an angle, do you get a different answer from cosine if you put into it that angle plus or minus 2 pi? Okay. If I go 2 pi around, do I get a different answer for cosine? Of course I don't, because I go right back to the same place. Right back to the same place. Same thing for sine. So what I just did didn't change anything. I really want you to understand. Isn't that the weird thing about trig? The sine of 30 degrees is the same thing as the sine of 390 degrees. Is everybody cool with what I just said? Because 390 is 30. Now I'm going to do some even weirder shit. Here we go. isn't this, is anybody having any trouble with me writing this? Let me start right here. I'm not done yet, obviously, but do you guys agree with me here? That's the same thing. What would you do with these powers?
Kill.
Multiply them, so that would cancel, you and get back here. So I haven't changed anything yet. I've just made it more complicated than I have to because I'm a math teacher and that's what we do. No, maybe. All right. So let me continue that streak. Here we go. Now watch this weird shit. I'm going to factor an n out, and it's going to be theta plus 2 pi k over n. I'm going to do the same thing over here. I need another parenthesis. Oh my gosh. Sine, factor an n out, theta plus 2 pi k over n. So it's kind of similar to this, right? But factor an n out, there's an n there. So if I put it back in, it would cancel, and I would get back to where it was. Okay, and keeping with tradition, I've run out of whiteboard. So let me come back up here. I kind of wanted this up here. Well, let's see. I've got it right here. I've got it right here. Do you guys remember what I said? If you see something to the n, cosine of n times angle plus I sine of n times angle, you could rewrite it like this. Yes, yes, and we all agreed, or at least nobody didn't disagree. Somebody help me out. Somebody's got a question in chat. What the hell is K? What is K? K?
Revolution.
Say, oh, okay, I like it. It's the number of revolutions. So all this is saying is go 2 pi k times. So if I start at 30 degrees and I go around 1,040,000 times, don't 1,040,000 full rotations, wouldn't I stop at 30 degrees? It's like I didn't go anywhere. That's why I love running on a track, and you're like, so much energy to go nowhere. It's awesome. Okay, I like it. I like it. I like it. I like it. I really want you guys to understand my point here. Can't I write this? Let me see. I think I do have enough room for this. Can't I write this as? All right, Jeff, you can do it, buddy. Are you going to do it? I am. Did I write that the wrong way around? I did. Let me do this one. Does it really matter which way these are? Can't they go the other way? Yeah, is that all right? Of course they can, because 1 over n times is still 1. Yes? All right, I just happened to write those the wrong way. I'm sorry. But wouldn't this be, isn't this something to the nth cosine of n times an angle plus I times sine of n times an angle? Yes? Isn't that what that is? Is the angle pretty? No, it's got a lot of shit going on. But isn't this just an angle? Yes. Isn't this just a number? Yes, to the nth power? Yes. So how can I rewrite this? Stay with me, stay with me. Isn't this going to be r to the 1 over n? I can write it like this. Times cosine of, you could do it, Jeff, theta plus 2 pi k over n plus I sine of theta plus 2 pi k over n. All, oh, you got it, Jeff. How many more you need? 1, 2. All to the nth power. No idea if you guys are still with me. If I see something that looks like this, I can write it like this to the nth power. I can take that n, I can take that n, and I can take that n out there. So I'm taking that n, taking that n, and taking that n out there. And then everything else is left inside. Oh shit, I'm sorry. I know, I'm trying to use every square inch of real estate that I have. All right, now I can get rid of this. Let me pull this up here. And again, this is just the derivation of the formula. You're not going to have to kind of do this over yourself unless it's a bonus question. So what do I have here? Can somebody help me out? If you saw, you could do it, Jeff. Go, Jeff. If you saw x to the 7th equals 11, how would you solve that? I know, but you, oh, I'm sorry. Okay, there you How would you solve that? What would you put in your calculator? How would you solve that? You could do it. Come on, you could do it. How would you solve that?
7th root.
7th root. Sorry, I can write it as 1/7. What if I saw x to the n equals 11? I can take the
And the root.
nth root. So look what I'm gonna do. All right. Don't I have z equals, let me just write this up here again. Oh boy, Jeff. All right. Stay alive a little bit longer, Jeff. You can do it. Oh my God. What are you doing, buddy? Give yourself a little room. All right, here we go. Here we go. You gotta go away. Can't I take the 1/n power of both sides? So a complex number to the 1/n, so the nth root of a complex number equals r to the 1/n, all this shit basically, cosine of theta plus 2 pi k over n plus I sine of theta plus 2 pi k over n there. Where k equals 0, 1, up to n minus 1. Is that right? Why did you forget that easy thing? I have no idea. I believe that's right. What makes sense, Jeff? I don't know anymore. I'm tired. That makes sense. Where are we? Yes, okay, yay. So let's try a problem, everybody. Let's try a problem. I can do erase this. Erase this. Okay. All right, here's a nice one. I want to know what the, yeah, let's start off with something nice. I want to know what the 1/3 power of I is, what the cube root of I. I want to know what that is. I want to know what that is. Bum, 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 bum. So the way to use this result is to first write this in R theta kind of form, right? All right, so I've got z equals 0 plus 1i. Do you see why that's a smart idea? Stay with me now. Is everybody with me? Somebody left. Oh well. How do I figure out what that looks like? I want to convert that to r cosine theta plus I sine theta form. So obviously, what do I need to figure out? I need to figure out r. That's easy. How to figure out r? What's the x piece?
0,
0. What's the y piece?
1.
1. So I get r is 1. That's nice. How do I figure out theta? And this gets a little interesting. You do it. You can do it. Can you do it? I thought I had faith in you. What's the y piece?
1.
1. Isn't tangent y over x? Is that what you guys are all worried about? Isn't that, what's wrong with that?
It's undefined.
That's right. The tangent of what angle is undefined?
When cosine is 0.
All right, when cosine is 0, and when is cosine 0?
Pi over 2.
Pi over 2, and why do I know it's not 3 pi over 2? Because 0, 1 is up here. So if you just graph this, you would know that it's at a 90-degree angle. Do you see what I'm saying? So of course the answer is pi over 2. If you just graph it, you can actually tell that that's going to come out to be pi over 2. So what does our complex number look like? It looks like 1 times cosine of pi over 2 plus I sine of pi over 2. Now, you have to force yourself not to simplify this, because then we're going to get here, which is this. I want to do a 1/3 power of I. That's the whole problem. I don't know how to do the 1/3 power of I. All right, so now I can do z to the 1/3 power. And now I can use this. It'll be 1 to the 1/3 power. Let me just go ahead and write that. Let me just go ahead and write that. So 1 to the 1/3 power times cosine of pi over 2 plus 2 pi k over n. Yeah, there n. What's n? N is 3. Plus I sine of the same thing. Everybody with me? I'm just plugging in here. Theta is pi over 2 plus 2 pi k. And n is 3. All right, Jeff, I think we got it. Okay. Now let's see this. Let's see. What do I get if k is 0? I've left myself no room. Let me erase this up here. If k is 0, what do I get? K is 0. I get cosine of pi over 6. Does everybody see that? Pi over 6. If k is 0, this is pi over 6. Plus I sine of pi over 6. That's the nice thing, is the angles will be the same. That's beautiful. Stay with me now. What's cosine of pi over 6?
Root 3 over 2.
3 over 2. Plus I sine of pi over 6 is 1/2. So this will be I over 2. Why not? So that if I cube this, my answer will be I. That's what that means. That's one of the cube roots of I. If k is 1, I get cosine of pi over 2 plus 2 pi over 3. All right, so pi, let's do this better, Jeff. Pi over 6 plus 2 pi over 3 is pi over 6 plus 4 pi over 6 is 5 pi over 6. So I get cosine of 5 pi over 6 plus I sine of 5 pi over 6. Okay, so all I'm doing is plugging shit in. You just got to be able to combine fractions, right? So that's all I did here. Pi over 6 plus 2 pi times 1 over 3. Like denominators, get it in there. That's 1. That's why this is so nice. Cosine of 5 pi over 6, just to cut to the chase, is negative 1/2. Plus sine of 5 pi over 6 is rad 3 over 2.
Then the opposite.
The opposite, thank you. I love it, Jeff. And then the last thing, now I know this is going to be the last thing, because k goes up to n minus 1. So they only got 1 left to do. If k is 2, then I get pi over 6 plus 4 pi over 3 is pi over 6 plus 8 pi over 6 is 9 pi over 6 is 3 pi over 2. Oh my God, I don't know if you guys follow me, but if you put a 2 in here, you get 4 pi over 3, which is 8 pi over 6 plus pi over 6 is 9 pi over 6 is 3 pi over 2. Oh, all right. So I get cosine of 3 pi over 2 plus I sine of 3 pi over 2. 3 pi over 2 is a beautiful angle. Cosine is 0. Sine is negative 1. So negative I is also a cube root of I. I don't know if you guys remember. Remember I cubed is negative I? Therefore, negative I cubed is I, which is basically what we just proved. Yeah, okay. So then we got the two other freaky ass answers. All right. Okay, maybe. All right. Okay, now, no, I'm not going to do that. Screw it. It's Thursday. I was going to lay a little groundwork for the next section, but I'm not going to. The next thing, listen to me now. I guess I will. Not as much as I thought. The next thing we're going to talk about is called parametric equations. Parametric equations. And what they are, they're so freaking cool. Somehow an Etch-a-Sketch comes into play with I can explain parametric equations using the idea of an Etch-a-Sketch. Does anyone not know what an Etch-a-Sketch is? Anybody? Or let me ask it this way. Does anyone know what it is? Maybe
Hell
that's
yeah,
what-
I do.
Is in the days before there were any Xboxes or shit around. We had to sit around and play with these little things.
I thought they were pretty cool.
Yeah, that's what I thought too here. Let me show you an example. Here's a perfect example. Where'd you go? Where'd you go? Come here. Where'd you go? Get away here. Stop doing this shit. Dadgummit. Hold on, everybody. Here it is. Come on, show me that one. There he is. All right, here we go. All right, just a second. I thank you, man. I understand the feeling. All right, there's Etch-a-Sketch. So when you turn the little knobs, one knob controls the up and down y-axis. The other knob controls the left and right x-axis. So it's all about, another way to explain parametric is, holy shit, that's $417. Anyway, sorry. I don't know what happened. Is it signed by Bob Ross? I don't know. All right. What was I saying? Shit. Oh, maybe. It's a very good point. Fuck, screw it. We'll talk about that on Monday. We're going to talk about it all on Monday anyway, so I don't know what I was about to say. So we'll see what that looks like on Monday. All right, guys, that's enough. Go have fun, do something. Let me know if you need to hang out. Otherwise, you're free to go.
Thank you for the lesson, Professor.
Sure. I get an Etch-a-Sketch now. All right, guys. I don't see anybody with questions. I'm going to head out.